Hello, good morning. This is Organic Chemistry Week 15. My name is Tim Braun, and it is June 9th, 2026. This is my presentation on the combined spectral problem. I was assigned group 14 with the molecular formula C7H14O2. And with the formula, the first thing I wanted to do was calculate the degrees of unsaturation, as this can give us information going into the spectra. So I took the 7 carbons, added 1, and subtracted the hydrogens divided by 2 from that, giving us 1 degree of unsaturation. So this is really helpful as we start to look at the spectra and estimate and guess what our compound might be, or the complete structure. Getting into the IR spectra, we notice first 3 diagnostic peaks. We have one at 3,000 centimeters, one at 1725 centimeters, and 1250 centimeters. And these correlate, according to the literature, to the sp3-CH stretch bonds, the ACO double bond stretch, and most likely a CO stretch. And the reason that we can estimate this as a CO stretch is we don't have any nitrogens present in the compound. And this value from 1100 to 1250 or 1050 to 1250 typically comes from a carbon bonded to a more electronegative atom. So we're going to take these values and our predicted bonds and place them down in our IR table. And we're going to re-verify the CO stretch bond and reaffirm that as we continue. Now we go to the CNMR table. We notice peaks at 170 ppm, likely from the carbonyl or from the carbonyl. We see a peak at 80 ppm from the CO stretch bond. We don't have any halides present alkyl halides present in the compound, and we don't have any nitrogen. So we can assume this is the CO bond here. And then we have 3 further peaks. So now 5 total. We know there's 5 unique carbons within the compounds. And these peaks are at about 20, 25, and 30 ppm. And as we start to put the structure together, we can better assign these groups. But this is kind of hindsight, the partial structures that I have written. So we can pretend like this isn't here for now. But we're going to take these values, write them down here on the left side, 170, 80, 30, 25, and 20. And then we can talk about right now the 170 ppm CNMR reading and kind of basically say that this is an ester, and we're going to talk about how we can say that. The other carbonyl containing compounds that we could have are, first, we know an amide isn't possible because there's no nitrogens in this compound, so we can eliminate that. We can look at the carboxylic acids and aldehydes and know that these aren't possible given our IR spectra. If we had a carboxylic acid, we would expect a really broad peak, probably present somewhere in this range, and it would be a little broader maybe. But from the 2600 to the 3500 range, maybe that whole area. But it's clear we don't have a carboxylic acid. If we had an aldehyde, we would expect a little peak probably right in here at about the 2750, 2850 range. And we don't see that either. We only see the 2900 to 3000 range peak. All right. The other compounds that we want to rule out, we already ruled out an aromatic from our degrees of unsaturation. And we know this can't be a ketone from the CNMR value itself. A ketone would appear in the 195 to 220 or 200 to 220 ppm range. So the only compound left that we can really attribute this bond to is the ester. And so this is an sp2C double bond to O. And then because we also have this CO sigma bond, we know that we're thinking that we have an ester now. We wouldn't be able to say this was an ester without this additional CO bond, but it really fits our chemical signature right now. And we're going to come back and talk about how we assign this bonding environment to these three values. But let's look at the HNMR spectrum. We have a bond at 4 ppm, or H. We have protons showing a signature at 4 ppm. We have protons showing a signature at 2 ppm, and protons showing a signature at 9 ppm. And then we also realize that these are all singlets. So we're going to start to take these values down here. And we have 3.92 and 1.2. And then we take the associated integration, and we mark those down. And then the multiplicity, which all appear to be singlets, which is actually very helpful and makes solving the problem a little bit easier because there's only a certain orientation that we can put together for this compound. So we'll start with the 9H values. Actually, let's start with the 3.9 ppm proton. So we're going to draw a compound that fits our spectra. We know we have an ester. For now, we'll leave that tail off. So we have to draw this ester backbone. And then this CO bond has to be present, but we also have protons that are attached to this carbon that are giving us the 4 ppm signature. And this occurs because the carbon is attached to the electronegative molecule. And then we also have to figure out where these 9 hydrogens are. We have another group at 2 ppm, and this is a singlet. Now, if these 3 hydrogens have a multiplicity of a singlet, they can't go on this side because this side would make these hydrogens have a multiplicity of triplet. So this spot fits really well with our compound. And it actually makes sense for our ppm value as well. This is a high ppm or downfield ppm value for a methyl group, but it's attached to a carbonyl carbon. So we would expect that downfield shift. And then on the other side, we need to have a spacer or another piece that would make these 9 hydrogens a singlet. And the other thing that we notice is that we have 5 carbons. So now we have 1, 2, 3, 5 unique carbons. I'm sorry. So we still, since these last 3 hydrogens are all the same, or the last 9 hydrogens are going to be equivalent in 3 different carbons, we have to add another carbon. And this carbon is called a quaternary carbon. It has no protons. This is the only possible structure given the spectra. And now we can go back to some of the CNMR 20 to 30 values and start to assign which carbons are going to receive which ppm. Okay, so now we have the equivalent hydrogens. Our hydrogen placements and orientation checks out. We've assigned the bonds to the HNMR spectrum, and now we have pretended like this is empty and we're going to fill this in. Okay, so the CH3 attached to carbonyl carbon is going to take the lowest ppm value. Now, why is this? The methyl that is adjacent to this carbonyl carbon is going to take the lowest value because this oxygen is more strongly pulling electron density. All right, and so the 25 ppm value shows a really strong peak. And we can leave the 20 for this methyl group because this 25 ppm has a really tall, strong peak, which indicate that our methyls are multiple or equivalent. That's what that tall peak tells us. So that fits with the 3 carbons on the methyl groups attached to the quaternary carbon. And then lastly, we have the quaternary carbon itself, and this is going to get a high ppm value because it has only C to C bonds. And so this is going to further shift it downfield. The compound is 2,2-dimethyl propyl acetate, and the common name is neopentyl acetate. And I have the drawing here. Thanks for watching.